You will recall in the last class we started doing this example of oblique incidence of a plane acoustic wave in between two medium. So, there was an incident wave A which was not normally incident between the two medium, and the objective was to find what are the transmitted and the reflected waves. In the last class what we did find was the angle of these two waves. The reflected plane wave would bear an angle theta r and theta I is the incidence angle. So, the angle of incidence was shown equal to the angle of reflection, and also we were able to prove the Snell's law in the acoustic context here, that is the angle at which the refracted ray or the transmitted ray bears with the normal to the two medium, that is called as theta t, and we had this relation which was shown to be the Snell's law. So, today we will just complete that analysis by possibly determining the two amplitudes. We are still to determine the two amplitudes, the reflected wave amplitude and the transmitted wave amplitude. So, we will start again with this problem. So, we have a medium 1 which is having the properties as rho 1 C 1 and medium 2 which is having the properties as rho 2 and C 2, right. So, you had an incident wave and the complex amplitude of that incident wave was given as A. So, what we have derived already is that the reflected wave will bear the same angle as the incident wave, which means in the region x less than 0. So, this is the interface is marked as x equals to 0. So, in this region which is x less than 0, you will have p x comma y given in the following fashion: a e to the power minus I k x x plus k y y, right. So, both the components in the x direction as well as in the y direction. So, this is my x direction and this is my y direction. Along both the components the wave is travelling in the forward direction. What has been shown in the last class is that the B wave will also have the same amplitude of these wave numbers, but it will have a sign reversal as far as the kx component goes, because the component of the wave travels along the negative x direction, not along the positive x direction. So, the B wave can be represented in this fashion: B e to the power I k x x minus k y y. So, here you realize that between the A and the B waves what we have is the wave number component in the y direction has the same sign, because both of them travels at least a component of these wave travels in the positive y direction, whereas the sign is flipped in the wave number component along the x direction k x. The magnitude remains same, because if the magnitude changes then the angle of incidence will not be equal to the angle of reflection. The angle of incidence equals to angle of reflection virtually gives us that the k x associated with the B wave will be same as the k x associated with the A wave. There is just a flip in sign which shows that it is traversing in the reverse direction along x. So, that is as far as the x directional x lesser than 0 region goes. In the x greater than 0, we said that there is a transmitted wave and we will denote this with C. So, the transmitted wave in this region can be represented as p x comma y as C e to the power minus I. The k x here will be different because the material is different. So, I will call this as k x prime here plus k y y. We have already shown that the k y corresponding to the region x less than 0 has got to be the same as the k y in the region x greater than 0. So, the k y has to be same, otherwise the continuity conditions will not get satisfied, which was what was discussed in the last lecture also. So, the k y corresponding to these two regions is same, but the k x is different, because finally k x square plus k y square has got to be equal to a constant which is omega square by c square. So, just to recapitulate, here you will have the condition k x square plus k y square is equals to omega square by c 1 square, whereas here you will have k x prime square plus k y square is equals to omega square by c 2 square, right. So, the fact that c 1 and c 2 is different is the cause of k x and k x prime being different, though k y's associated with these two regions are same. So, again we will appeal to the continuity condition at the interface between the two fluids, but in the region of medium 1. Here we will get A plus B into e to the power minus I k y y, right, by substituting x equals to 0, right. And on the from the other side, what we will get is P at 0 plus is C e to the power minus I k y y. So, that again establishes the fact that k y between these two regions has got to be the same, which was anyway proved earlier. So, now if these two pressures have to be the same, so by continuity of acoustic pressure, across the interface, what we have is A plus B must equals C. This is our equation 1. This kind of equations we had already seen even for the case of normal incidence, right. So, that part is nice and simple. Remember, our objective is to determine B and C given A, right, or the ratio of B by A or C by A. So, towards that end we have got one equation, we need one more. So, we will now appeal to the equation for continuity of velocities, right, and this time again it will be the continuity of velocity along the x direction, right, because velocity along the y direction can still be different, because you are assuming the viscosity to be negligible in the case of acoustic derivations. So, we will appeal to the continuity of velocity along x directions, and you will recall we had already derived the relation between pressure and velocity along any specific direction, which was something like this boxed equation. So, u x equals to k x divided by rho 0 omega into the pressure amplitude, that gives us the appropriate direction of the velocity. So, we will use this condition now to work out the velocity of in the two regions. So, u x in the x y region corresponding to x less than 0 will be given as k x divided by rho 0 rho 0 here would stand for rho 1, because I said that the density in medium 1 is rho 1, right. So, rho 1 by omega into A e to the power minus I k x x plus k y y. But for the B wave it will be the other way round, because the B wave is having the component along the negative x direction. So, that will have a minus sign. So, minus k x divided by rho 1 omega B e to the power I k x x minus k y y. This is as far as x less than 0 region goes, and for x greater than 0, this is u x x comma y is going to be k x prime this time, because the expression involves k x prime. The wave number associated in the x direction is denoted as k x prime for the region of x greater than 0, the right hand region if you might so wish to call it, and the density in this region is rho 2. So, that changes things. So, C into e to the power minus I k x x plus k y y, right. So, again we will establish the continuity condition at x equals to 0. So, at x equals to 0 we could pull out k x by rho 1 omega a minus b into e to the power minus I k y y, right, x equals to 0 has been substituted. And in the region x greater than 0 at x equals to 0, if you wish to find out this value, that is also pretty simple, k x prime by rho 2 omega c e to the power minus I k y y, right. So, at the end of the day you need to equate these two, which means a minus b must be equal to c into k x prime rho 1 divided by k x into rho 2, right. Omega is same between the two, and thankfully we already have established k y between the two regions x less than 0 and x greater than 0 has got to be the same. So, that also does not bother us. What we are left with is a minus b into k equals to c times this factor, which is k x prime into rho 1 divided by k x into rho 2. Okay. And this is our equation 2, and if we look back at equation 1, we had a plus b equals to c, right, which is what our equation 1 was. So, if we use these two equations, we could easily relate c in terms of a. So, that reads as 2 a is equals to c into 1 plus k x prime rho 1 divided by k x into rho 2. So, that implies c as 2 a divided by 1 plus k x prime rho 1 divided by k x rho 2. So, this is how we get the transmitted wave amplitude in terms of the incident wave amplitude. You could also find b as c minus a, and that is also not too difficult to work out. So, you can pull the a outside, 2 divided by 1 plus k x prime rho 1 divided by k x rho 2 minus 1, and that comes out as a 1 minus k x prime rho 1 divided by k x rho 2, and the denominator would read just the same, k x prime rho 1 divided by k x rho 2. Okay. So, these are the two expressions for the two wave amplitudes, the reflected wave amplitude and the transmitted wave amplitude. So, please recall when we did normal incidence between the two media, we had the ratio in terms of rho 1 C 1, right. You might think, why is that rho 1 C 1 ratio getting changed to this k x prime k x is coming instead of rho c. So, that is not difficult to understand. If you recall that k x prime is omega by C 2, sorry, k x prime is, okay, I will do this in a different way. So, recall for normal incidence, the reflection ratio was shown to be dependent, reflection and the transmission ratio were shown to be dependent on the characteristic impedance. Okay. This was the crucial quantity, and you will recall characteristic impedance was given by rho c. Here what we are seeing is it is the ratio that comes back here for the case of oblique incidence is seen to be k x prime by rho 2 or k x by rho 1. So, wave number along x direction divided by the density of the fluid medium is what seems to be thrown at us. But if you realize that for normal incidence, so note for normal incidence what is the associated k y? What will be k y for normal incidence? If it is incident not obliquely, but directly in this form, then what is the associated k y? 0, right. So, for normal incidence k y turns 0, which implies k x for medium 1 is going to read as omega by C 1 and k x prime for medium 2 is supposed to be omega by C 2, because either ways k y is 0. And if you make these substitutions back into this expression, so then again you will get to see that if I copy and paste this expression, let us say, so this expression will be reading 2a divided by 1 plus, instead of k x prime I have to write C 2, rho 2 and C 1. So, I have written instead of k x prime as omega by C 2, instead of k x I have written omega by C 1, and then the two omegas have cancelled each other. So, again we get back the ratio of impedances, which is what we expect for a normal incident case. So, we have also shown that from the oblique incidence you could recover back the results of the normal incidence, because normal incidence is after all a special case of oblique incidence. Oblique incidence is more general. Also there are other features like total internal reflection, which I think it is pretty easy to understand. Again you can looking at this relation, you will be able to find out that this I mean going again using the argument similar to geometric optics, from this relation it is clear that the transmission angle will prevail only if sin theta t is a number which is less than 1, right. But looking at this, it is pretty clear that sin theta t will depend upon C 2 by C 1. So, if C 2 by C 1 ratio is pretty high, there is a possibility that the sin theta t term turns more than 1, in which case there is no real theta t, which means that there is actually no transmission that is happening. There is only an evanescent wave, which is what we will describe. So, that aspect is called total internal reflection. I will just leave with this comment that this aspect is just the same as you would have studied even in geometric optics, right. But it is nice to see that we could derive these results, which were sort of axioms in geometric optics, from a very fundamental approach based on the mathematical theory of wave propagation of plane waves, right. So, I think here we will close our discussion associated with oblique incidence. We will move on to another crucial idea, that of evanescent waves, and to introduce that idea we will firstly have to have a brief discussion about flexural waves or bending waves. Till now we have been talking about acoustic waves. So, we will take a slight detour and talk about the waves in a beam, for example. Similar waves will also exist for plates. After all, plates are the two dimensional counterpart of beams. So, if you recall the governing equations of motion for a beam, equation of motion for a beam is given as E I d 4 w d x 4 equals to q, where q is the load intensity or load per unit length. E I is the flexural rigidity, and W is the transverse deflection that we are interested in for a beam, right. This is called the Euler-Bernoulli beam, which is really good enough for our discussion, right. And in case you want to look up how this is derived, look at any book in like such as Timoshenko's book or Boresi's book, right. These books will have the derivation of this equation. So, we will pick the thread for our purpose from this governing equation. We are not going to derive this governing equation, because that I presume is almost an undergraduate affair. So, we will pick up the thread from this governing equation. This equation is the way it is written in here, it is applicable to statics, but to move from statics to dynamics is a very easy extension. So, to formulate the equations for dynamics, we need to introduce inertia forces. So, the only change that we will make at this stage, wherein we are looking for the free vibration problem, in absence of any forcing, we wish to see whether there is a possibility of obtaining any solution for this equation, right. So, the only force that we will include is the inertia force. So, we are looking at the free vibration, as we iterated a few lectures back. For free vibration, there is no external forcing that we need to account for. The only forcing that has to be accounted for in this term Q is going to be the inertia force, and the inertia force will be minus m times del 2 W del T 2, right, where m is the mass per unit length, because as we said that Q is the load intensity, which is the load per unit length. So, similarly, we will have to take out the inertia force per unit length, which is why we have to take m as mass per unit length. So, this in terms of density would be the density times the area of cross section. Okay. So, this time we will start using partial derivatives, because now we are saying that for dynamics we are going to have this W dependent upon two variables x and t. For statics, it is obvious W depends only on x, there is no other independent variable which is appearing in the statics problem. But for the dynamics problem, there are two variables, namely the spatial variable and the time variable, which is what you have seen even for the acoustic pressure. Even for a one dimensional case, you looked at that there was an acoustic pressure which was dependent on both on x and t. So, with that, the equations of motion for free vibration of a beam is given as E I del 4 W del x 4, and I am changing to partial derivatives from the ordinary derivatives. That will be minus m del 2 W del T 2, right. There is no other forcing that we are interested in other than the inertia forces. Now, let us look for a harmonic solution. So, we look for a harmonic solution, just the same ideas as we did in acoustics. So, once we say that I am looking for a harmonic solution, W x comma t will now take a form W x into e to the power I omega t. So, omega is the associated frequency, right. So, we are hoping that we are able to find some non-trivial solution of this system, which is of this form. W x comma t is W x, which is a function which is as yet unknown, times e to the power I omega t, right. So, if you make such a substitution, again there once you play your card of the temporal dependence to be a harmonic, then the only variable of the only independent variable that is left in your problem is again x. So, there is no need again to go to partial derivatives, because the only variable that we have is x. So, we might as well say that this is an ordinary derivative, because this is the only independent variable that is left in the problem after invoking the harmonic dependence as e to the power I omega t. And you know that once you have selected a harmonic dependence, you take derivative once, it has got to be I omega times the function itself, and if you take derivative twice, it is I omega times I omega, which means minus omega square the function itself, right. So, here what will happen is, because of two time derivatives, you are essentially going to get a product of omega square, m times omega square, the minus sign will cancel with the minus sign that is sitting here. So, m omega square w is what you will get. So, del 2 del T2 of w is minus omega square w, if you wish to call it that way, right. So, this is the equation that we need to solve. At this stage we are looking for a harmonic solution, and we are looking for a we are looking for solution at each omega, right. So, now we make even one more bold assumption, that we are looking for a wave solution, for a wave solution. So, what does that mean? W x, because we have already invoked the time dependence as e to the power I omega t, therefore, W x also has got to be a complex exponential, because only then it will remain a wave, right. As we have seen in acoustics also, the wave solution essentially means the temporal dependence and the spatial dependence has to be of the same form. So, what we are looking is a function of this form, possibly with some constants, because this is a linear equation, into e to the power k x, right, or I k x I should say, because e to the power I omega t is the complex dependence that we have taken for the time variable. So, if we invoke this now, what we get is I k whole to the power 4 E I, which is the flexural rigidity, multiplied by W must be equals to m omega square W, and this implies that E I k to the power 4 must be equals to m omega square. So, just to recapitulate what we have done, our objective was to find whether or not it is possible to get a wave solution, or rather a harmonic wave solution to the beam equation, right. Accordingly, we invoked two substitutions, one in time, one in space. In time, we took the substitution for the temporal functional dependence to be of the form e to the power I omega t. In space, we took the substitution as e to the power I k x. And now, what we are seeing is that yes, it is possible that you will get a harmonic plane wave solution associated with this beam, provided the k's and omegas are related through this equation, right. So, in other words, if k is m omega square by E I and fourth root of these numbers, then you are going to get a wave, right. So, let me write this note for you. So, inference harmonic waves are possible at any frequency omega provided or rather instead of saying provided, the associated, once you say it is a wave, there are two things that you must say, one is the frequency and the other is the wave number. So, associated with the frequency omega there is a harmonic wave, and the wave number of this harmonic wave is going to be k, where k is given by that equation, right. So, the associated wave number of this harmonic wave is k, where k to the power 4 is m omega square by E I, right. The same thing we have seen in acoustics, but in acoustics the relation was associated with each frequency omega, you are going to get a harmonic wave with wave number k, where k is k square or k is basically omega by c. Here we are having k to the power 4 is m omega square by E I. But please note, there is one stark difference which I do not know whether you have realized. This is going to give 4 roots, this is not going to give 2 roots. Last time for acoustic waves we have seen that there are 2 wave numbers that is possible, plus omega by c and minus omega by c, and the interpretation of the 2 roots was pretty easy to understand, that one of them travels in one direction, the other travels in the other direction, right. But here we have slight difference in this wave number equation, and this difference is due to the fact that k comes with the power 4. So, therefore, essentially there are 4 roots to this equation. What are these roots? So, let us say that the 4th root, let us call kb as the positive 4th root of m omega square by E I. That means, as you take the square root in your calculator, if you take the square root twice, the number that you get is kb. So, then the roots of k will be kb minus kb, but also ikb and minus ikb, right. So, the 4 roots of k would be in this form, where kb is just the 4th I mean square root taken twice, and if kb is denoted by just the positive real 4th root of the equation, then there are 3 other roots, which is minus kb, ikb and minus ikb. So, if we put each of these back into our system and let us try to interpret this solution. So, accordingly, what are the waves? The waves are w x comma t, either is a e to the power I omega t plus kbx, or you could have a e to the power I omega t minus kbx. I think I better write this way. Or you could have a e to the power I omega t plus I kbx, or you could have a e to the power I omega t minus I kbx. It did not come out within the allotted space. So, I would just need to shift this a little bit. Okay, so that was easy. A e to the power I omega t minus I kbx, right. So, these are the 4 solutions that are possible as per our derivation. Now, let us look at the physical inference associated with each of these solutions. The first 2 are pretty easy. The first one is a backward travelling wave, right, because it has the same sign in time as well as the phasor has the same sign in time and space. So, this is a backward travelling wave. So, how about this one? The second solution that I have written down is a forward travelling wave, that is also no big deal. The third and fourth looks a little odd, but let us sort of open this up a little bit. So, what we have for this expression is the following: a e to the power I omega t and e to the power minus k b x, right. So, therefore, what we see is actually here we will have in if we plot out this in terms of x at any specific time, we are going to see that it will decay as we plot in the positive x direction, right. So, this is a decaying wave, whereas what was the plot of this backward travelling wave and forward travelling wave showing? It was showing that the amplitude remains constant with time as well as space, right. Whereas here we see that the amplitude actually falls off with space. It is not the wave is getting generated at some point, but it is not being able to travel at that fixed amplitude. It is rapidly decaying, it is exponentially decaying in the positive x direction. What is happening associated with this? This wave can be opened up as following: this will bear a positive kbx, right, minus I square here. So, minus I square is plus 1. So, you will get e to the power I e to the power plus kbx, and kb as per our notation is a real positive number, right. So, therefore, the plot of this, if this is the direction of x, it will actually decay in the negative x direction. So, that is actually natural justice. If you take a wave component to be decaying in the positive x direction, by symmetry there has to be a wave component in the negative x direction also, right. So, instead of saying that it is growing in the positive x direction, we would prefer to interpret this as decaying in the negative x direction, and we will I mean if as the course probably matures, we will see what are the applications of these decaying components, right. But at present we are definitely convinced through our mathematical derivation that if we are looking for harmonic plane waves, then not only is there a possibility of travelling waves which keeps on travelling at constant amplitude, but also there is a possibility that these travelling waves rapidly decay as they propagate, right. We will always interpret the direction of travel associated with the direction of decay, right, at least for now. Otherwise, we may be misled to think that some waves are actually growing in amplitude as they are travelling, that is physically not plausible. So, we will rather interpret the e to the power minus kbx as the one which decays in the positive x direction, and e to the power plus kbx as the one which decays in the negative x direction, instead of doing it the other waves. So, what we are going to call for these two waves is the following. So, this is an evanescent wave, this is called an evanescent wave, both of these are evanescent waves. They are actually not travelling waves. Travelling waves, as we have studied in great details, will have these characteristics that it will have the same nature when it propagates. The amplitude should not fall with distance, whereas here we are saying that the amplitude falls off with distance. So, just to give you a feel of what will happen, though we will not do this derivation, at least not at this stage. If you have an infinite beam, just like we studied the infinite acoustic duct at the first instance before going to the finite duct. If you have an infinite beam system, and infinite beam systems are not that impractical. If you think of these transoceanic pipelines, they are like infinite structures, because virtually it is very long. So, if it is excited somewhere, then obviously now at whatever frequency of excitation you excite this, you are going to expect that there will be some waves which are going to get generated, right. By physical plausibility condition, you are going to expect only a travelling wave in this zone which travels in the positive x direction. You are not going to expect a backward wave in this zone, because that is physically implausible. There is no reflection that is going to happen, the source is at the middle, this source can at the most create a forward travelling wave in this region to the right of the excitation. In the region to the left of the excitation there will be only a backward travelling wave, there cannot be a positive travelling wave because there is no reflection, there is no excitation which is on the left side of it, right. But then what you will see is that using just these two waves, just these two travelling waves will not be able to satisfy the boundary conditions associated with this point. What are the boundary conditions? The boundary condition is that there is a jump in shear force of the beam and that jump in shear force has to account for this excitation force. The shear force has to change, right, because only then the jump in shear force, the discontinuity in the shear force diagram is essentially equal to the applied force, right. Because you have an applied force there is a jump in shear force. So, there is a jump in shear force, but there is no jump in the bending moment because there is no applied moment. And so, you have to essentially satisfy 4 conditions at this point. I am calling this point x equals to 0. So, at this point x equals to 0 you need w 0 minus to be equals to w 0 plus, that means the displacements from the two sides must match, right. You must also have the slope from the two sides to be matching, you must have the moment from the two sides to be matching, but you must have a jump in the in the shear force to account for the fact that there is an applied excitation force which is F, right. So, you would need to satisfy 4 boundary conditions in order to solve this problem. Using just 2 travelling waves you will not be able to satisfy all the 4 boundary conditions, right. So, you have to satisfy the only way that is left and that is what comes out through our mathematical derivation is to account for these 4 boundary conditions with not just these 2 travelling waves, but 2 evanescent waves also, right. So, these 2 travelling waves with the 2 evanescent waves. So, totally we are having 4 waves, right. So, all these 4 waves will combine in the right proportion such that all these 4 boundary conditions get enforced. Because there are 4 waves, 4 boundary conditions can get satisfied, whereas in the case of acoustic pressure you had a acoustic equation, you had the case where you had just in the case of acoustic pressure you had a second order equation, and because it was a second order equation you could not satisfy I mean you could satisfy only 2 boundary conditions for the acoustic case, whereas here for the beam equation it is a 4th order equation, and also from physical principles it is well known there are 4 associated boundary conditions, and the 4 conditions can be satisfied only if there are 4 waves to choose from. And over and above the 2 bending waves, 2 travelling bending waves, we get these 2 evanescent waves, which sort of is a nature's way in which these boundary conditions can get satisfied, right. So, in case you are interested to look at this derivation, you can look at DJ Mead's book on passive vibration control. This full derivation is given. This book is called Passive Vibration Control by DJ Mead. Okay. Okay. So, but as we said we are just going to look at the bending waves, because we need to understand one crucial these aspects even in the acoustic parlance, which is what we are going to head towards. So, what we understand is that there are 4 wave numbers which will get triggered at every frequency, and this equation by the way which relates the wave number to the frequency is called the dispersion relation. So, the relation between the wave number k and the frequency omega is called the dispersion relation. Okay. Sometimes in some books it is interpreted as the phase velocity with respect to speed, but even the wave number and the frequency is also a dispersion relation. There are many ways in which we can interpret this. I have not come yet as yet to phase velocity concept, but we will do that in a moment. So, the dispersion relation will present us in the form of a graph which is omega by k. And what we have just now seen for a flexural wave is that we will have k to the power 4 is equals to m omega square divided by E I, which means k is proportional to square root omega, right. So, this is just the real part, real positive wave number that I am plotting. Similarly, the others can be plotted, right. So, k versus omega plot is what we have arrived at. Just to reinforce what we had for acoustics we had k equals to omega by c, right. So, k equals to omega by c is what happens for acoustics, and that dispersion line is pretty simple to draw. So, this is what we will get for acoustics. So, I will call this dispersion relation for acoustic 1D plane wave. This is what has already been derived. Now, this crossover point is very interesting, and this frequency is called coincidence frequency. Okay. And it turns out, and we will do that derivation in the next class, that sound radiation actually happens only for these frequencies, whereas in these frequencies sound radiation is almost negligible. The actual sound radiation happens only for these frequencies. We will come to why probably in the next class, but just before we end this class, a short story to motivate you the idea that we are coming to. You have all learnt about this bell jar experiment, right. So, in the bell jar experiment you had some sound source which was enclosed over a bell jar, and then progressively it was evacuated, right, by using a pump, right. And then it was told to you that as the evacuation is happening, the material is being withdrawn, which means that the sound is growing feeble, and that is what was observable, right. So, that is well known, but in a modification to it, what we do is we withdraw the air, but we replace the air with, let us say, hydrogen, and this experiment was actually conducted, right. I will give you the references, I will give you the paper also. So, if you put back hydrogen now instead of air and put this hydrogen back at the same pressure, same atmospheric pressure. So, you cannot now say that the chamber is evacuated. The chamber is having the same pressure as the air should have, but just that the medium has changed from air, it has become hydrogen. What actually happens is the sound grows even more feeble, right, and that the reason for all this to be happening is because of that coincidence frequency. So, as has been reported in the literature, this is what we call the coupling between the vibration and the sound. So, as I said, without proof though at this stage, that the vibration happens only for frequencies beyond the coincidence frequency. The sound radiation for a given vibration happens only for frequencies beyond the coincidence frequency. So, once you replace these two medium, it does happen that this coincidence frequencies gets changed, and only the components of waves which are supersonic, which are having wave numbers below the acoustic wave numbers. So, these are the acoustic wave numbers, only radiating components of the structure will be in this zone, which is below the wave numbers associated with the acoustic wave numbers. Only those wave numbers will radiate, others will not. We will come to the proof of this aspect in the next class again, and again I will come back and explain this observation, that why is it that hydrogen will not be able to radiate sound into the air despite holding the atmospheric pressure at the same value as it is with air. Okay, but for now we will stop here. Thank you.